Okay, so this is section 5.4, day 2, and we're gonna start looking at that connection between integrals and derivatives. So the essential question for today is, how is the antiderivative used to evaluate definite integrals? So if you recall, we've been evaluating definite integrals using fint on our calculator for quite a while now. Now we're going to tie in the relationship with the antiderivative that we were talking about in chapter 4. So let's kind of start by looking at an example that we've had in the past, and that is using the area model strategy to evaluate this definite integral. So we have a function here. This function is 2x, and we want to evaluate the definite integral from 1 to 4. And we know that that means we're going to accumulate a region between the function 2x and the horizontal axis. And that region is going to start at 1 and end at 4. And we want to know in this case, since it's above the x-axis, the area of that region. And so evaluating this integral then becomes a problem of finding the area of this shape. The shape is a trapezoid, or we can think of the shape as a rectangle plus a triangle. And so as we're looking at figuring out that region, then I'm going to take the rectangle here, which is 3 by 2, and I'm going to add to it the triangle, which is half base of 3 and height of 6. And so the definite integral here has a value of 6 plus 9, which is 15. And so now we're going to accomplish the same thing by using what I call the antiderivative strategy. There's a little asterisk right here. We're going to rename this in a couple of slides. So the antiderivative strategy says, let's evaluate this definite integral by doing what we did in chapter 4. So chapter 4 says that we look at this expression and we say, what function can we think of that has the derivative 2x? So if you think about what we can differentiate and get 2x with, that function that we can differentiate and end up with 2x is x squared. So that's the big F of x. It's the antiderivative. So if you look at that antiderivative, x squared, and you tie in the starting point of 1, that's where the area starts, and the ending point of 4, then if we substitute 4 into x squared, we get 16, and that's close to the answer. And if we substitute 1 into x squared, we get 1. And so with a 16 and a 1, we should be able to make a 15 by subtracting them. So what we figure out then is that if we take the big F, which is the antiderivative, evaluated it at the right bound, or what we call the upper bound, but it's the right side of the shape, and we subtract the antiderivative, big F, evaluated at the left end of the shape, or the lower bound, then we end up with 15, which is the actual value of the definite integral. So the solution goes something like this. We found the antiderivative, we found that function, then when differentiated gives us 2x. So that function is x squared. So here's the antiderivative. This vertical line here means evaluated at. So this whole expression reads x squared evaluated at 4 and 1 equals, and then we know that the answer equals 15. So what we do is we substitute in the upper bound 4 squared, and we subtract the expression we get when we substitute in the lower bound, 1 squared. So we get 16 minus 1, which is 15. And so this antiderivative strategy leads to the same answer as the area model. And that will happen every time. So now, instead of relying on geometric shapes, we can find antiderivatives. And so we can extend this then to be used on functions that don't make geometric shapes. And now we have a strategy to work with those functions as well without a calculator. So the asterisk, if you notice, it showed up here too. because that antiderivative strategy is really called the fundamental theorem of calculus part 2. And so the fundamental theorem of calculus part 2 goes kind of like this. We have a little f of x, we know that's the derivative, and we want to integrate it starting at a, which is the left side of the shape, and going to b, the right side of the shape. And so in order to find that value of that region, we find the antiderivative, big F, we substitute in b, evaluated at b, and we subtract the antiderivative, big F, evaluated at a. And so that's the fundamental theorem of calculus, part 2. And so what we have to do then, if you look at this polynomial, we can see we've got several powers on our x variables here. So we have to look at this, and we know that that finding the antiderivative is reversing the derivative process. So if we think about that, we should be able to come up with a process or a strategy to find the antiderivative of each one of these terms. So this is also known as the integral evaluation theorem. That's another word for the fundamental theorem of calculus part 2. So if we, to reverse the power rule, before we start diving into that, let's think about the power rule a little bit. So if we think about the power rule a little bit, when we have something like x squared and we want to take the derivative of that, we reduce the power by 1, and then we multiply by the old power. So the derivative of x squared becomes 2x. So if I want to do the antiderivative, I have to reverse that, which means everything I see here, I'm going to do the opposite of. So instead of reducing the power by 1, I am going to, on my x term, instead of reducing this, instead of making this power 1 smaller, I'm going to make this power 1 bigger. So I'm going to increase the power by 1 instead of reduce. So that's the exact opposite of the exact reversal of our differentiation. And then instead of multiplying by the old power, I'm going to do exactly the opposite. Instead of multiplying, I'm going to divide. And instead of using the old power, I'm going to use the new power. So I'm going to divide by the new power. So that's the reversal of the power rule for any exponential term, for any term that has an exponent. So let's try that reversal on this expression. So I want to integrate the polynomial, x cubed plus 3x squared minus x plus 5, and I want to evaluate it between 0 and 2. So let's first start with this first term. So this first term is x cubed. So my power rule reversal says increase the power by 1, so that's x to the 4th, and divide by the new power. So I'm going to divide by 4. And then I'm going to go on to the next term and do the same power rule on that. The next term has a coefficient of 3, so we're going to leave the 3 there. We're just going to kind of leave it alone for a second while we do the reversal of the power rule on x squared. So we bump up this power by 1, making it x cubed. We divide by the new power 3. We have some simplifying here to do, but we'll wait to do that until in the next step. So now let's go on to the next term. I have a minus sign, and this term x here, that's really x to the first power. So when I bump up that power by 1, I get x squared, and I'm going to divide by that new power 2. And then I've got a plus sign, and then integrating 5, 5 is really 5x to the 0 power. So if I bump up that power by 1, it's x to the 1 power. So this last term, the antiderivative ends up being 5x. So I've reversed the power rule on every term. Now I'm going to kind of bracket this off here. And then this is my evaluated at sign again. I kind of just included it in the bracket. And so we're going to evaluate it at 2, and then we're going to subtract what we get when we evaluate it at 0. So in order to evaluate it at these, remember the 0 is the left side of the shape and the 2 is the right side of the shape. So to evaluate it at 2, I just have to plug 2 into each one of those x locations. Before I jump into that, let's do that simplifying I mentioned a little earlier. So 3 divided by 3, that simplifies. So after we simplify that, that's just x cubed, and everything else doesn't really need simplifying. Now I'm going to go ahead and plug in 2. So I've got 2 to the 4th over 4 plus 2 cubed minus 2 squared over 2 plus 5 times 2. And then I'm going to subtract, and I'm going to plug in 0 everywhere. And you notice when I plug in 0, every term ends up being 0, but I would like to plug it in just to kind of show you. So this whole expression on the right is going to end up being 0, and this on the left over here is going to end up equaling 20. So 2 to the 4 is 16 divided by 4 is 4 plus 8. That makes these two make 12. And then I'm going to subtract 2. That's going to make 10. Plus 10 is 20. So this definite integral then has a value of 20, which means that's really the region between the function and the axis from 0 to 2. So at this point, we're just going to try our fundamental theorem of calculus part 2 on 6 examples. And we're going to focus on powers, and we're also going to try some other functions. So the first one we have here is 4t minus 1 quantity squared. And we do have a chain rule for integration, but it's not something we're going to talk about for a little while. So when we see something like this, the first thing we really want to do is FOIL it out. So that ends up being 16t squared minus 8t plus 1 dt. Notice the variable is t here. We just treat it like an x. The variables will change, but really the process stays the same. So I have another polynomial, just like the one before. And I'm just going to go ahead and reverse the power rule. So let's start with this first term. I'm going to put the 16 out there. And then I'm going to do the reversal of the power rule here. So I'm going to bump my power up to 3. And I'm going to divide by that new power 3. And I'm going to go on to the next term. So I got a minus 8 here. I'm just going to keep that out front. We'll worry about simplifying in the next step. And here's my t. That's a t to the 1 power. So when I bump up my power, it becomes a t squared. I'm going to divide by that new power 2. And then I have a plus, and bumping up this power of t is going to be just a t to the 1st power. And so I'm going to evaluate that from 0 to 1. Looking at this is 16 thirds. I can't simplify here, but we can simplify here. So let's go ahead and simplify that to minus 4t squared. And now we can go ahead and put in the numbers. So I'm going to go ahead and substitute 1 in here. So I've got 16, 1 cubed over 3, minus 4 times 1 squared, plus 1. And then I'm going to go ahead and subtract the expression when I substitute in 0. And notice when I substitute in 0 everywhere, each term ends up having a value of 0. So that whole right-hand side goes to 0. And so evaluating this, and this is where we have to kind of get good at fractions. And so I'm going to kind of give you some strategies for that right now. So 16 times 1 cubed is 16, so this ends up being 16 over 3. And this ends up being minus 4 and plus 1, and that makes minus 3. So I have to take 16 thirds and subtract 3. So the 3 I'm not going to think of as a whole number. I'm going to think of it as 9 over 3. That way the denominators match. So now I can just do this. So it's a little strategy of thinking of whole numbers as fractions. So now I can just do 16 minus 9, which is 7. So this answer is 7 thirds. So the definite integral for number 1, the answer is 7 thirds. For number 2, we have x raised to a power, but the power is a fraction. And that's okay. We still have that strategy of reversal of the power rule, and that works for fractional powers. So we're going to deal with more fractions here. So we're going to take x and we're going to raise it, and that power is going to be 1 bigger than 2 thirds. So when you look at the power here and you think 2 thirds and look at this answer here, 2 thirds plus 1 might be difficult to think about, but 2 thirds and then thinking of 1 as 3 thirds might make this answer make a little more sense. So 2 thirds plus 3 thirds is 5 thirds. So that's my new power, and I'm going to divide by the new power, 5 thirds. And I'm just going to leave it like this for this step. Looks a little messy, but we'll clean it up in the next step. And we're going to evaluate this from -1 to 1. And so now we know that when we divide by 5 thirds, it's the same as multiplying by 3/5, that reciprocal. So here's a rewritten form of that, which might be a little easier to evaluate. So now we're going to substitute 1 in here. And then we're going to subtract the value when we substitute -1 in here. And so 1 to the 5/3 is just 1. So this first set of brackets ends up being 3/5. And we have a minus sign. And then -1 to the 5/3 power is -1, right? The cube root of -1 is -1, and that to the 5th power is -1, times 3/5 is -3/5. So we have 3/5 minus a -3/5. That's the same as adding. So the value of the definite integral here for number 2 is 6/5. For number 3, we have this expression here. It looks kind of messy, but we're going to distribute the square root of w into the brackets here. And so remember, the square root of w is w to the 1/2 power. So when I distribute it, I'm going to write this as 3 times w to the 1/2 power minus, and this is w to the 1st power times w to the 1/2 power. So remember, we add our powers there. So that's going to be w to the 3/2 power. So 1 plus 1/2 is 3/2. And so now that I have 2 terms, I can just go ahead and reverse that power rule on each term. So for the first term, I've got a 3 coefficient that I'm just going to kind of let hang out there. And then looking at the w to the 1/2 power, bumping this up by 1 means adding 2/2. That makes sense. So 1/2 plus 2/2 is 3/2. And I'm going to divide by that new power, 3/2. And this looks messy, but that's okay. We'll clean it up in the next step. And then I have a minus sign. And now I need to reverse the power rule on this. So I've got w to the 5/2, right? 3/2 plus 2/2 is 5/2. And I'm going to divide by that new power, 5/2. And again, it looks a little messy, but that's okay. We'll clean that up in the next step. And then we're going to evaluate that at 4 and at 0. So let's take this first term here. Dividing by 3/2 is the same as multiplying by 2/3. And when you multiply by 2/3, so we have 3 times 2 divided by 3. The 3's are going to cancel, and we're going to end up with 2w to the 3/2 minus, and then dividing by 5/2 here is the same as multiplying by 2/5. So we get 2/5 w to the 5/2. Now we can go ahead and put our limits of integration in there. So for the upper bound for 4, remember that's the right-hand side of the shape. I'm going to put a 4 in here, so I'm going to have 2 times 4 to the 3/2. And remember, when you're looking at this expression, it's only the 4 that's raised to the 3/2, not the 2. Okay, we're just raising that variable to the power. The 2 is just a coefficient that we have to multiply in at the end. So the order of operations where we have to do our powers before we're multiplying, that's pretty important. We've got a minus sign here, we have a 2/5, and then we have a 4 to the 5/2. We'll worry about evaluating those in a second. I could have put brackets here too, probably wouldn't have been a bad idea. And then we're going to evaluate this at 0. So I'm going to put 2 times 0 to the 3/2 minus 2/5 times 0 to the 5/2. And if you notice, each term's got a 0 multiplied into it, so that whole thing is going to be 0. So let's talk about evaluating these 2 terms. 4 to the 3/2. 4 to the power of 3, that's what that means. And then 4 to the power of 1/2 means the square root. So let's do the roots first, which means working with the denominator of this fractional power. So what is the square root of 4? That's 2. And 2 cubed is 8. So 4 to the 3/2 must be 8. And then times 2 is 16. Now let's look at this next term, 4 to the 5/2. So again, the the 1/2 power, the 2 in the denominator of this power here means the square root of 4, which is 2. So we really have 2 to the 5th power here. 2 to the 5th power is 32. And then multiplying 32 times 2 gets us 64. So we have minus 64/5. So we have to evaluate that. So here again, we have a number plus or minus a fraction. So we want to think of the 16 kind of like the previous page, where we want to think of this as a fraction. So we want this over 5, which means we have to multiply the top by 5 to write it with a 5 on the bottom. So we're not going to think of it as 16, but we're going to think of it as 80/5. That means the same as 16. So now it's easier to subtract those tops. So 80 minus 64 is 16, so this must be 16 over 5. Moving on to number 4. Notice I snuck a trig function in here. So we have to think about what function gives us a derivative of cosine. So as we integrate this, the integrating 6 gets us 6x. Finding that function where the derivative is cosine means I have to take the derivative of sine. So the integral of cosine is sine. And then I'm going to evaluate that expression at pi over 2 and 0. So when I plug pi over 2 in here, I get 6 times pi over 2 plus sine of pi over 2. And then minus, and then I'm going to run out of space, so I'm going to put it down here, 6 times 0 minus sine of 0. I just didn't have space to squeeze all that in here. So 6 times pi over 2, so if we notice again, I use a lot of zero lower bounds just because it makes the math a little easier as we're beginning to learn this. Just means we're always starting from the origin location. This whole second thing is going to be 0, because sine of 0 is 0. So we can eliminate that for the time being. 6 times pi over 2 is going to be 3 pi. And sine of pi over 2, think of the unit circle here. I'll kind of draw it in space. The unit circle, pi over 2 is up at the top. Sine is the y-coordinate. So we're talking about that top value. The y-coordinate is 1. So it's going to be, the answer for this definite integral is going to be 3 pi plus 1. For question 5, now we're still dealing with powers, but they're powers in the denominator. And in order to reverse the derivative rules, we really need to have that in the numerator. So in order to write that in the numerator, if we want to relocate this, we want to give it a negative power. So we're really being asked to do the power rule on x to the minus 2, and we can do that. We can do the power rule on every power value except 1, and that's going to be this last example here, and we'll figure out what to do there then, in a few minutes. So let's do this power rule here. So we're going to bring the 3, put the 3 down. We'll deal with that later. Now let's do the power rule here. Negative 2, we're going to bump up that power by 1. Getting bigger means moving to the right on the number line. So 1 bigger than negative 2 is negative 1. So we have x to the negative 1 divided by negative 1. And we're going to evaluate that from 3 to 6. So let's simplify this. First of all, x to the negative 1 can go back down in the denominator as x. And then we have 3 times negative 1. So in other words, this minus sign can be put out here. So we have minus 3 over x evaluated from 6 to 3. So 3 is the left part of the shape, 6 is the right part of the shape. So substituting in 6, we get minus 3 over 6. Minus, substituting in 3, we get negative 3 over 3. And so we end up with negative 3 over 6 is negative a half. Minus a negative 3 over 3, that's minus a negative 1, so it's plus 1. So the value of this definite integral then is a half. So that brings us to our last definite integral example, and that's this one. X is in the denominator again, so we're going to rewrite this with a negative exponent. And then something a little strange is going to happen. As we try to do the power rule here, we'll put the 4 in, and then we'll do our power rule on x to the minus 1. So 1 bigger is x to the 0. That's okay. But when we try to divide by that bigger power, we run into a problem. We can't divide by 0. That doesn't give us a defined value. So now we have to think a little bit. Going back up to the original expression here, this is really 4 times 1 over x. And so we have to go back and kind of like with the sine and the cosine. Can you think of a function that when we take its derivative, we get 1 over x? And we had an inquiry-based activity using nderiv to discover what that was. And that was the natural log of x. So when we take the derivative of the natural log of x, we get 1 over x. So this definite integral ends up being 4 times the natural log of x. And we're going to evaluate that from 1 to 3. So we're going to plug in our upper bound, our upper limit 3, and then we'll plug in our lower limit 1. and the natural log of 1 is 0, so this whole thing goes to 0. So the value of this definite integral ends up being 4 natural log of 3. So there are 6 examples, and they're pretty closely tied to what you're going to see on the homework tonight. So how is the antiderivative used to evaluate the definite integral? We know that the antiderivative, if it's a power, it's a reversal of the power rule. Sometimes when it's not a power, we have to work backwards with sines, cosines, other trig functions, e to the x, ln x. So we have to remember how to reverse those derivatives to get antiderivatives in order to evaluate the definite integrals. So that antiderivative is used then to set up the evaluation process for the fundamental theorem of calculus part 2. So at this point, you can go ahead and start day 2 on the homework. If you're going to try to test out with the Blackboard quiz, you can wait to do that until we get to day 3.